I'm Andy Sayler. I've been working on this with my advisors, Eric Keller, and Dirk Grunwald. We're from the University of Colorado Boulder, and our project's called Jobber. The goal is to essentially automate Inter-Tenant trust in the cloud. So we started out by asking how we can make the data center more efficient, more secure, but also more manageable. In particular, we were looking at these issues because we know cloud use in enterprise and beyond is growing rapidly. Forbes puts it at 50% a couple months ago and rapidly increasing. There are a myriad of platforms available to us, and those are only growing as well. And not only are we using the cloud in growing frequency, but our cloud workloads are increasingly inter-tenant. Some recent research in SDI puts all data center traffic, 10 to 40% of it, as being inter-tenant traffic. So we're using the cloud more, and our workloads are just interacting within the cloud more. So it starts to make sense to ask if there's a way to improve the efficiency of this inter-tenant traffic, if there's ways to optimize for it, and systems we can build around treating it in manners that make more sense than the way we're doing it today. So examples of this kind of inter-tenant traffic could be things like ad network to web hosts. So I'm hosting a website in some data center, and I'm serving ads from an ad network that's also in the same data center. I could be loading those ads from a server that's sitting in the same rack as me, and it would be nice if we could do something special and leverage that fact that we do have this inter-tenancy and some abilities to do more than we can normally do with it. This could also be things like CDN to ISP communication, where you have an ISP loading data from a content distribution network to then push out to their customers. And as the good Mr. Snowden has recently informed us, this could even be things like the NSA sitting around in my data centers, and I'm sending some data to them upon their forceful request. So we have a number of situations where this inter-tenant traffic inside a data center makes sense. But unfortunately, most of the data center research thus far has been on isolation. When we talk about data centers, we talk about how do we isolate our virtual machines? How do we make sure nobody else can see my traffic? And all of this, while helpful in some cases, just serves to kind of hinder this inter-tenant traffic as well. Essentially, we're treating all traffic as untrusted. We don't have any mechanism right now to say, well, I am sitting in the same rack as this ad network who I'm constantly loading traffic from. Maybe I should privilege that traffic in some way. I shouldn't necessarily have to treat that traffic, analyze it in the same manners that I would analyze untrusted traffic from the general internet. So we've dealt with some of these problems before. I mean, we have things like business-to-business relationships where you get a bunch of lawyers together and they sign some papers, and I manually configure my firewall to allow traffic from a specific host in my own data center elsewhere on the internet. I tunnel that traffic. I have these kind of privileged VPN-type relationships. But this is full of manual and static configuration. And we know that one of the major problems in security is misconfiguration. Often when our security systems break down, it has little to do with the underlying security primitives or issues in them, and everything to do with the fact that some administrator configured it wrong. The cloud only exacerbates this issue. In the cloud, we have virtual machines popping in and out of existence with regular frequency. Manual and static configuration in the cloud really does not make sense anymore. So we would like to be able to do inter-tenant optimization, but we don't want to have to just manually do it for each tenant with which we kind of would like this privileged level of cooperation. So the combination of all these issues means that the way we're treating clouds today leads to a lot of extra overhead. We're treating this inter-tenant traffic that we'd maybe like to trust in the same manner we're treating external traffic. We're passing it through firewalls, through intrusion detection systems. In the cloud, this is costing us extra money, extra compute resources. It's prone to error. If we have to try to get around some of these issues by using manual configuration, then we've just added one more thing that could go wrong when we misconfigure it. And it's full of untapped potential. If I'm sitting in the same rack as someone who I'm loading the bulk of my website content from, it seems a shame that I can't somehow leverage the fact that we have this very high-speed network connection. We're sitting in the same data center, maybe even the same rack, so on and so forth. And if I'm just passing all that traffic through my firewall like I would normally pass untrusted traffic, then there's some there's some potential there that I'm not leveraging. So instead, we'd like to find a way to optimize trusted traffic. So if I am sitting in the same data center and I can identify a series of flows as trusted, then I would kind of like to privilege that. I would like to have it bypass my edge security apparatus. Maybe it goes through its own separate security apparatus, but I am giving it some level of privilege that I don't have to treat it in the same manner I'm treating other traffic. Of course, we still want to filter untrusted traffic. We're going to have a lot of traffic both within the data center and outside of the data center that we can't identify as trusted, and that we want to continue to pass through any kind of edge security that we require. But we'd like to do all of this automatically. We want to remove this manual static configuration aspect that is so prone to error and really doesn't fit well with the kind of ephemeral nature of cloud infrastructure. So toward this end, we've proposed Jobber, which is our network security architecture designed to handle the volatile nature of the cloud and kind of optimize these inter-tenant communication. So Jobber is an architecture. We've worked on a prototype implementation of it, but we feel there's probably other implementations that would be equally as valid. So as an architecture, it has a few key components that kind of allowed us to build it up. The first of these components is we need a way to securely designate trusted and untrusted traffic. We need a way to make this designation within the cloud. So we've turned to the concept of trust networks. Trust networks have existed for a while. There's a variety of systems out there to kind of do this trust network concept. We're using a trust network called Introduction-Based Routing, and I'll cover the details of that momentarily, but you've also seen trust networks on things like, based on things like social relationships, trust networks based upon behavioral reputation. You could really use a variety of kind of these underlying systems to build a trust network. We've chosen IBR, but there's not to say there aren't other components that could also satisfy, or other implementations that could satisfy this component. So for those of you that aren't familiar with introduction-based routing, because it is kind of key to how the rest of our infrastructure works here, the core concept behind introduction-based routing is your decision on whether or not to trust someone isn't based upon your opinion of that person directly. Instead, it's based upon your opinion of an intermediary who's going to be making an introduction on their behalf. So to take a quick example, if we have three hosts like this, Q, M, and G, and Q and G both have existing trust relationships with M, but not with each other, and we have a situation where Q would like to communicate directly with G. Well, that's not allowed off the bat because Q and G don't trust each other. But what Q can do is it can go ahead and turn to host M, who does trust it, and say, hey, M, you trust me, can you introduce me to G? And if M does in fact trust Q, then it's going to go ahead and say to G, hey G, this person who I already trust would like to communicate directly with you. I would recommend that you trust them because I trust them. Now, if G trusts M, it's going to take this knowledge as being valid and say, okay, well, you trust them, that's good enough for me. Now I will trust them as well, and Q and G can establish this direct trust connection. The core concept behind IBR is that it incentivizes only making good introductions. If you're host M, you don't want to introduce Q if you think he's going to misbehave. Because when this connection breaks down, be it for valid or because Q does something like starts to attack G, whenever they decide to end this trust connection, both Q and G send feedback to M. And if Q was misbehaving, G's going to say to M, hey, I'm not going to trust you as much anymore because the person you told me to trust turned out to be untrustworthy. This then hurts M's ability to get its own trust connections in the future, diminishes its standing within the network. So there is kind of this economic model that comes into play that encourages you to only make introductions on the behalf of people you actually trust. We feel this economic model meshes really well with kind of the economics of the data center, and that's part of the reason we've chosen IBR. So moving beyond trust networks, next we need a way to kind of automatically ascertain track reputation. Trust networks give us a way to spread reputation, but we still need an underlying primitive to base kind of those initial decisions off of. We know that our networks today have a variety of sensors throughout them. We have logs on individual host machines. We have logs on things like routers. We have a variety of things like intrusion detection systems that give us data about the current state of our network and the behavior of people on it. And we have a lot of systems that's kind of designed already to gather up this data. We have open source frameworks like Nagios. A lot of individual cloud platforms provide their own frameworks like Amazon's CloudWatch. And then there's a variety of custom solutions out there. The age of big data makes it very easy to take this huge amount of information we have about our networks and kind of try to aggregate it down into specific data points. So we've taken that last approach and kind of built our own framework. It starts out similar to what like an Nagios might do by exposing this generic interface that you can just feed data into, data from a variety of sources, things like syslog, intrusion detection systems, other stuff on the network. The goal here is just to gather as much data as we possibly can. We then pass that data through a couple of other layers, the first of which is just designed to kind of sample and throttle it, and the next is designed to classify the behavior. So this is the layer where the administrator says, these kind of things on the network are bad, these kind of things on the network are good. Our system can basically take in all that data, sort it into good and bad, and you can get more fine-grained than just those binary designations if you so wish, but it tries to classify that behavior. We then, because we want to kind of turn this eventually into a per tenant reputation data point, we aggregate that data based upon the tenant that's associated with. So we can associate a host of virtual machines with a specific tenant. We can then, based upon the behavior of those machines, start to build a reputation for that tenant. We then expose all this data through just a standard interface that our jobber system can query to say, hey, give me the reputation of this specific tenant, and kind of trickled up based upon the underlying data from the network, we can generate this reputation for each tenant that we've interacted with or that we've seen traffic from in the past. So the final component that we need for Jobber is a way to control all this. So we have a way to determine to come up with a reputation for each tenant. We have a way to kind of propagate that reputation. But now we need a way to actually act on that information. We need a way to steer traffic either through these trusted or untrusted paths, or various levels of trusted paths if you want to go more than just the binary route. Fortunately, we live in the age of programmatic routing. Things like software-defined networking has given us a lot of tools for programmatically changing the routing state of our network, programmatically steering traffic through the network. We have things like OpenFlow today. Really, there's pre-existing systems that allow you to do things similar to this, things like MPLS and GRE. We've also seen a lot of cloud platforms offer their own APIs. So EC2 has its virtual private cloud concept, which gives you an API into its routing tables. And most specific network hardware vendors these days have their own APIs as well. So there's a lot of options when you want to programmatically control routing on the network. We've built our system around kind of SDN concepts using the Floodlight OpenFlow controller, and then we've done a lot of our prototyping in the Mininet kind of emulation environment. So we've taken the SDN approach to controlling routing on the network and kind of to make these actions happen once we know what we want to happen. So these three Jobber components kind of lead to a variety of Jobber architectures that we can then leverage as well. And there's a few things we want to consider when we talk about each architecture. The first of which is we have some architectures that are appropriate for legacy data centers that you could deploy today in EC2. Then we also have architectures that are appropriate for what we would see as the data center of the future that can kind of integrate Jobber at a lower level, but does maybe require some modifications to the way data centers operate. We also have to look at whether or not it requires you to modify each individual host. Obviously, there's a larger barrier to the initial deployment if you have to go and install some new piece of software on every virtual machine in your cloud network. So we have architectures that both require you to do that and avoid needing to do that. We want to look at whether or not the routing is active or passive, whether or not each individual tenant has to kind of push these routing decisions up, or whether or not the data center can kind of make the routing decisions on behalf of the tenant, and the tenant can be more transparent to the tenant. And finally, the downside to using IBR is it does kind of have this problem of traditionally it's a distributed system, and finding a valid trust path in a large distributed system can become computationally difficult. Fortunately, in the data center, we do have the possibility to maybe do some kind of a centralized view of the whole network. We do have a data center provider who can maybe see everyone, and is there a way we can leverage that to reduce the computational difficulty of a lot of these traditional IBR type decisions? So the first architecture we propose is appropriate for legacy data centers, but it does require host awareness. In this kind of an architecture, we envision, for simplification, just two tenants running a couple of virtual machines, and we have a situation where tenant B wishes to communicate with tenant A, or one of tenant B's virtual machines wishes to communicate with one of tenant A's virtual machines. Initially, this traffic flows through tenant A's standard edge security system, and the Jobber client running on each individual virtual machine on tenant A can then identify this flow and say, hey, I have this incoming connection. Let's find out if it's something I can trust and something I should privilege. It contacts its local Jobber server, who looks up the reputation of the other tenant, communicates with any other Jobber servers that are required. If there are more than two tenants, this would involve that IBR handshake where we have to dance through a series of intermediary tenants to find a trust connection. To simplify the example, we'll just assume two tenants, and we'll assume that they do trust each other. So if they do trust each other, the Jobber servers can basically negotiate and say, okay, we're going to allow this to be a trusted flow. They then talk down to both their clients, and the clients in each individual virtual machine can essentially set up a tunnel or open up the appropriate firewall ports, do whatever they need to do to basically allow this direct interaction between machines. So this architecture is nice because it's deployable today, but it also has a series of downsides. It does require us to make each individual virtual machine Jobber aware to kind of set up these tunnels at a very low level within the network. It has no concept of passive routing. It still requires each individual tenant to really, manually open up individual firewall ports, manually tell the other tenant to re-steer where it's sending its traffic to. And it still has no concept of central IBR coordination. If we had to dance through 10 different tenants in order to find a trust path, this would start to become computationally difficult, and setting up that initial trust connection can start to take a lot of time and a lot of effort. So we've proposed another architecture that's still appropriate for legacy data centers, but this time we removed the requirement on host awareness. In this example, we'll assume we're operating on something like EC2 or some kind of a platform that provides a programmatic routing API. So in EC2, this is the virtual private cloud system, and that's an API Amazon provides to essentially allow you to update routing tables within your set of virtual machines. Like before, tenant B wants to communicate with tenant A, but this time the jobber server can kind of detect it without having to talk to the client directly. It can be querying our security mailboxes to look for these kind of flows, and when these flows occur, it can do the appropriate handshakes to establish a trust path. If a trust path can be provided, now instead of having to alert the individual virtual machine, the virtual machine can be agnostic to this fact. The tenant itself can start re-steering the traffic just by updating its routing table via virtual private cloud for that tenant. So if these can be trusted, we go ahead and tell tenant B, okay, this is now a trusted connection. Tenant B updates its virtual private cloud routing table, and we can now start steering this traffic directly to the virtual machine in question, bypassing kind of our edge security, open up the appropriate edge firewall ports or whatever we need to do to make this happen. If it's going to be a tunnel, there's a variety of ways you can kind of implement the underlying semantics here. So like before, this is deployable today. We can do this on something like EC2 as long as we have this kind of API. It no longer requires us to modify the host directly. Instead, the individual virtual machines can kind of be agnostic to what Jobber's doing here. It operates now at the tenant level instead of directly at the host level. But we still don't have any concept of passive routing. Each individual tenant has to kind of manage its own routing tables. And we still have no kind of central IVR coordination. So our final architecture is one that isn't necessarily appropriate for data centers today, but could be appropriate for the data center of the future if we kind of make the data center natively Jobber aware. So in this kind of a situation, we imagine an SDN-based data center that has some kind of a data center-wide SDN controller, and that controller can be running Jobber as one of its kind of controller-level applications. So in this situation, when tenant B goes to communicate with tenant A, we now pass just through the standard switch infrastructure for our data center. But now the data center itself can kind of recognize this flow as being an inter-tenant flow and can see if it can find a valid trust path for it. So in this situation, the data center recognizes this inter-tenant flow and it goes, okay, well, let's see if the various hosts involved will trust this. So it goes and asks each tenant involved whether or not they want to trust this flow, or in an IVR, if there's more than 2 tenants, again, asks the necessary tenants to get an introduction. If all the tenants on the trust, if it can establish a valid trust path, now the data center directly can simply start re-steering these flows and on behalf of the tenants start sending this traffic directly to an internal virtual machine or directly bypass kind of the standard edge security mechanisms that would be required. The other advantage here is we can leverage the fact that we have this data center-wide view to really reduce the complexity of finding a valid IVR trust path. The data center knows all of its tenants on board. It can immediately compute any valid trust path kind of between them and then ask each tenant individually whether or not they want to actually allow that. So the data center is kind of facilitating for us here. It's important to note we're still leaving the actual decision of whether or not they want to trust these flows up to each tenant. Each tenant still maintains their own reputation of other tenants, so we don't necessarily want to push that reputation up into the data center. We want to allow each tenant to make these decisions for themselves, but we would like the data center to start kind of facilitating these on the tenant's behalf because it adds a lot of nice properties. So it's not necessarily deployable today. We don't have data centers that kind of provide this Jobber as a service notion that just tell you if you stand up a Jobber server and tell me where it is, then I will try to optimize these connections on your behalf. So we couldn't necessarily roll it out today, but if we did modify our data centers to support this, it does have a variety of other nice properties. We don't have to modify our individual VMs. The routing is now passive. The individual tenants don't have to worry about maintaining routing tables to allow this. It's all done at the data center level. And we can kind of leverage the data center's centralized view of the whole network to really optimize these IVR trust paths. So where are we at right now? This is somewhat early phase work. We've been working on it for just under a year now. We've completed architectural design of the variety of architectures you just saw, and we've built kind of proof of concept prototypes to prove out all the underlying technologies within each design. We're currently working on completing a full system prototype of that final SDN architecture, since we feel that's really the strongest architecture in the long run. And then we're also building partial prototypes for the legacy architectures just to prove out how you could do it on EC2 today using virtual private cloud like we discussed a minute ago. We have not yet completed a prototype to the point where we can do a full-scale performance analysis. That's obviously, part of the reason we want to justify this is we'd like to say that you could, in fact, reduce the the overhead required by kind of optimizing these inter-tenant flows. So we'd like to we need to do some further work to actually prove that out, to take the performance numbers. And we've also said that this makes it easier to use because we can do a lot of this automatically. Obviously, that would require some usability analysis to really back up those assertions. So we start out by asking how we can make the data center more efficient, secure, and manageable. We feel that Jobber provides ways to do all of these things. We provide efficiency by allowing us to optimize these direct inter-tenant communications to really kind of securely take advantage of the fact that we're sitting in the same data center as a lot of the people we're interacting with, and we would like to treat that traffic in a manner differently than we treat just untrusted traffic from the internet. We provide security by kind of leveraging this introduction-based routing and reputation concepts to automatically and dynamically propagate security without the network and avoid the static configuration. And we help manageability by avoiding the kind of static configuration of the past and doing a lot of this automatically to kind of automatically, if the administrator just basically sets up a list of good and bad behaviors and a few basic primitives like that, Jobber can automatically build up a dynamic trust network on top of that and maintain it as the cloud changes, as VMs come in and out of existence, so on and so forth. So with that, I would like to open up for questions. I also have some things that you can ask me about if you don't have things to ask me about. So thank you very much, and questions.
We have some time for questions. So I have two. So the first one is, what is your adversary model? So I would imagine that to create this secure communication framework, you have to assume a certain kind of adversary. And a related question is, what is the trusted computing base? So for example, where are the routing agents located, and are they also susceptible to certain kind of attack? So basically, these two are related questions. So I would like you to.
Yeah, of course. So the adversary model, to some extent, Jobber's kind of defined to support some flexible adversary models. Obviously, so we've talked about Jobber optimizing inter-tenant flows. You could actually use it to optimize any flows, be they within the same data center or not. The reason we kind of focused on inter-tenancy is because the data center is where it's kind of easier to calculate these trust networks. Obviously, maintaining a trust network for the entire internet is probably intractable. Maintaining one for the people you communicate with in your own data center is maybe more manageable. So we assume a situation where you're communicating with a lot of other services in the same data center as you, and in general, these services are probably trustworthy. The things like ad networks that you have a relationship with, but it's possible they could be compromised. So your ad network could get hacked, and you don't want to necessarily start allowing it to attack you just because you've said, oh, I'll always trust this network. That's kind of where the dynamics come in. We want to maybe, initially we're somewhat liberal in who we trust, but then we're careful to monitor that traffic as it's still occurring and cut off those trust connections if one of these other tenants in the same data center that we're trusting becomes compromised, or if they start behaving in a manner that we don't necessarily think they should be behaving in. So your second question, based upon the trusting computed base, it kind of depends on which architecture you're using. Obviously, in the final architecture, you have to trust your cloud provider. If they're the ones that are kind of facilitating these interactions on your behalf, it does require saying, okay, I'm going to trust Amazon to do this honestly. We have started to, I mean, it's, again, earlier phase work, but we would like to get to the point where maybe we can say, well, what if you don't trust Amazon? Is there a way to kind of double check some of these things it's doing? Is there a way to confirm the decisions it's making and cut off certain things if the data center itself starts misbehaving? But yeah, the trust computing is somewhat architecture dependent. And in the last architecture that we liked the best, I mean, it really does require trusting your data center provider is kind of the core of it. And then trusting your own Jobber server with each tenant. They're providing this server that tells the data center whether or not it wants to accept trusts. Obviously, if that itself becomes compromised, then you can no longer trust any of the output that it's giving you.
So in your SDN-based design, do you also have to trust the guest operating system inside those virtual machines?
Not necessarily. Well, I mean, it depends what you mean, right? So if someone compromises that operating system, there's a variety of other things they could do. This maybe doesn't, I mean, that would open up a variety of attacks that this may or may not stop, right? Like if someone else owns that box on there, you may be steering trusted traffic to it, and now maybe that box starts attacking somebody else. Someone else could then realize that they're being attacked, and Jobber would then cut off access to that box to other people. Whether or not it identifies that on your behalf, kind of would be maybe not. I think it depends upon the nature of what someone does with that compromised box and whether or not the kind of Jobber sensor framework or whatever you're looking at on the network can detect what they're doing.
Other questions from the audience? If not, I have one more. So there's still time.
Do you want to go to the microphone so that the recording?
Right. So I'm also, this is interesting, right? So the thing is, I wonder what is the scalability of this approach, especially incurred by the introduction-based routing. So I know that this is work in progress, but do you at least have some preliminary performance data that you could share with us at this time?
Well, so a couple of points. So introduction-based routing, and not necessarily, it's not our work that says this, but the kind of underlying IBR work, does tell us that there is a computational complexity to kind of establishing IBR trust paths in the traditional sense. Traditionally, IBR is fully distributed. It has no centralized concept. So there is a scalability issue if you don't have any kind of centralized view to basically finding a trust path. It becomes very difficult to say, well, I mean, I may know who I trust, but if I have to do 4 or 5 hops to find a trust path, you can do a little bit better than brute force, but it does start to become complicated to figure out who I need to ask for an introduction, to ask for an introduction, to ask for an introduction, to actually establish that trust path in the long run. So that's part of the reason in our SDN view we combat that scalability concern by kind of saying, well, we are in a data center now. We do have the data center provider, and we can use them as kind of a global view of the data center. They can track who's trusting who at any given time. So the data center provider can theoretically find a more optimal path than I would be able to find myself without a global view. So one way we've tried to help IBR on the scalability front is to kind of push up to the data center the decision as to establishing the trust path for me. As far as preliminary performance data goes, we've done, like I said, the proof of concepts that are basically SDN based on top of Mininet. Because it is SDN based, the place you pay the overhead is at the start of any flow. So when you first establish the trust connection, there is going to be some extra latency occurred. It need not actually be extra latency, because at worst case, it's going to perform like it would perform if you weren't trying to trust it at all. But there's the initial overhead of actually establishing that trust path. Once you do, Jobber doesn't really add any more overhead. Once the trust path has been established and you update your routing tables, then it's no longer, there's maybe some monitoring going on, but we assume you can monitor without adding overhead. So I don't have hard numbers, but the goal would be in the long run it would add very little overhead at all, and any overhead would be a one-time cost at kind of the start of each flow. So if you have long existing relationships like you would with an ad network or someone you're constantly serving from, you may have to pay an upfront cost, but kind of regardless of its size, that upfront cost probably becomes negligible in the long run.